Hello everyone, welcome to my second video on existence theorem. So we saw in the previous video, we saw intermediate value theorem, IVT, that was our first existence theorem. Well, technically our second if you count extreme value theorem. Now we're looking at in this sequence of videos, our second existence theorem, which is Rolle's theorem. So Rolle's theorem states that assuming that we have a function which is continuous, so again, just like IVT, we have a continuous function defined on a closed interval AB. And now we're adding differentiability. So we have a differentiable function on the open interval AB. So we could take the derivative of the function on the open interval AB such that f of a equals f of b. So for IVT, f of a and f of b have to be on different, they have to be different essentially. Whereas here now, for Rolle's theorem, f of a and f of b have to be equal. So the endpoints have to be on the same horizontal line. And if this occurs, then there exists a number c in the open interval AB such that f prime of c equals 0. So we're not going to look at the proof. The proof is fairly simple. You guys could do it on your own. You have to break it up into 3 cases. But we're going to look at the idea. So the idea is, let's consider the function. Let's say this is the y-axis, x-axis. We have some point here. We'll call it A. B is here, it's on the same horizontal line, so f of a equals f of b, so this is the same line. What we're saying is we're going to connect these two lines with a continuous function, these two dots with a continuous function, and at some point we're going to have some value in between a and b where its slope of the tangent is 0, or its derivative is 0. So let's say I connect it like this. Well, if I connect it this way, notice that at the highest point here, we know that we have a horizontal tangent. So if we call this value here C1, f prime of C1 is equal to 0. The slope of the tangent line here is 0. And same for C2. This point here, called C2, we have a horizontal tangent. F prime of C2 is 0. So the only way to connect, at some point when we connect these two dots by some function that's continuous, we need continuity, there's going to be at least one single value, at least one, we could have multiple, where its derivative is equal to 0. Okay, so I challenge you to connect these two dots with a function where the derivative is not 0. Okay, how would we do that? So you might be thinking, well, what if I connect this point here, my A, with this point here, my B, with just simply a straight line? This is f of A, which is equal to f of B. Whatever that value is, it's the same. So it's a straight line. Do we have a point where the derivative is equal to 0? Well, think about it. When you're connecting these two lines over here, these 2 points with a line, all you did is you created a constant function. And we know from the beginning of the semester that the derivative of a constant is 0. So here, any point that you take, if you take its derivative because it's a constant, it's going to be 0. So Rolle's theorem still holds for this straight line. No matter how you connect these 2 points, at some point, there's going to be a point on the function, a c value, where its derivative is equal to 0. That's Rolle's theorem. So let's go ahead and look at examples to apply Rolle's theorem. So in our first example here, it says to use Rolle's theorem to prove the equation has exactly one root between 0 and 1. And the equation that's given is x to the 5 plus 5x equals 5. So we actually saw this exact equation in the previous video when we applied IVT. The difference being is, first of all, if it doesn't say to use Rolle's theorem, we know we have to use Rolle's theorem because it's stating to find that this equation here has exactly one solution, opposed to the last time when we saw it in IVT, it says to prove that the equation has at least one solution. Okay, so make sure you distinguish the difference. Here we have to show that there's exactly one. There's only one solution. There's only one x value that's going to satisfy this equation between 0 and 1. So let's go ahead and start it off. So the way you start this off, we actually saw this already. You begin by applying IVT. So you apply IVT first to show there exists at least one. Okay, and then we're going to apply Rolle's theorem using an argument by contradiction, showing that there cannot be two. Okay, so let's go ahead and do that. So let's repeat this argument with IVT. So first of all, we consider the function x to the 5 plus 5x minus 5 equals 0. We're not going to write equals 0, but we know it's equal to 0. So we bring the 5 over because we want this equation here equal to 0. So we consider this function. In order to apply IVT, we know the function has to be continuous on a closed interval. So do we have continuity? Well, the function is a polynomial. Since the function is a polynomial, we do have continuity. That's fine. So the continuity is done. And now we need to choose a value that's, we're going to replace our x values and get one that's positive, one that's negative. So we did this already. Plugging x as 0 gave us a negative value, and plugging f as 1 gave us a positive value. 1. Okay. So this was done in the previous video, so I'm not going to repeat it. We got a negative value, we got a positive value. Therefore, we know. So by IVT, we stated that there exists, backwards E, that's there exists a C in between, in this example, 0 to 1. So in between the two values that we chose, 0 and 1, there exists a C value such that ST such that f of C equals 0. Okay, so we said there exists at least one root. So now we want to show that there cannot be more than one root. Now this is where we apply Rolle's theorem. So the way we do this is we argue by contradiction. So we state that let's pretend there's two roots and see what happens. So suppose there exist two roots. Let's see, let's call them, I don't know, E. Okay, let's call them M and N. Suppose there exists two roots, M and N. So if these are roots, this means that these are solutions to this equation up here. Suppose there exists two roots, M and N, such that if these are roots, then f of m equals f of n are equal to 0. Okay, so these are solutions to this equation up here. So suppose there's two of them. If there's two of them, and also m and n have to be in the interval from 0 to 1. So this is a side note. And there exists two roots m and n in the interval from 0 to 1 that we're using, such that f of m equals f of n. This is equal to 0. Then what Rolle's theorem says that if there's two roots, then there has to be a point in between the roots where the derivative is equal to 0. The function is continuous, f of x is continuous, and it's differentiable. We have continuity, we checked that already. Is it differentiable? Could you take the derivative of a polynomial? Yeah, we know how to do that. So it's differentiable, that's good. And here we have f of m equals f of n. So we have 2 points, they're both equal to 0. So if we sketch this quickly, this is 0, this is 1. We're saying there's 2 points in between 0 and 1. Let's call this m, let's call this n. Since they're both on the same line, they're both equal to 0, the y values are equal to 0, then the function has to pass through both these points. If the function passes through both these points, there's going to be a point in between them where its derivative of some value, let's call it z, equals 0. Okay, so then by Rolle's theorem, there exists a z in between the two values where its derivative is equal to 0. So by Rolle's theorem, there exists a z in between the interval m and n such that f prime of z equals 0. Okay, so let me just erase this. So this is the argument that we're making. If this is true, then this has to be true. But let's go ahead and see what happens with the second derivative. I'm just going to erase this. Oh, sorry, not the second derivative, the first derivative. If this is f of x, this implies that f prime of x is equal to, if we take the derivative of this, it becomes 5x squared, 5x to the 4 plus 5. Okay. What's the issue with this? We're looking for an x value that's going to be equal to 0. What x value could you put in here that's going to make this whole thing equal to 0? How could you do that? Well, you can't. That's the issue with this. This is the point where we get a contradiction. There's no value of x that you could put in here to make the whole equation equal to 0. Why? Because we have x to the 4. This whole term here, 5x to the 4, is always going to be positive. Positive or 0. Okay, it has to be greater or equal to 0. The smallest value you can put in here is 0. If you put a negative value in here, because it's to the exponent 4, it's going to turn out to be a positive number, and then you're multiplying it by 5. So this is a positive value, and then whatever positive value, or if you get 0, that's the lowest value you can put here, you're adding 5 to it, which makes it not equal to 0. This could never be equal to 0. There's no value that you could put in here that you can replace x with that's going to make it equal to 0. So there cannot be a z value where when you take its derivative, it's equal to 0. So we obtain a contradiction. Okay, this is the argument that we're making. So by Rolle's theorem, we arrived at a contradiction. So this means that our initial assessment, or our initial assumption that we made that there exists two roots is not possible. We arrive at a contradiction. Therefore, we cannot have two roots. Hence, we have exactly one root, right? If you can't have two roots, you can't have two or more, because you don't have two. So we have to have exactly one root, and we're done. Okay. So in this next example here, it says to use Rolle's theorem to prove the equation has exactly one solution. The equation that's given, cos of x equals 4x. So pause the video, try to see if you could solve this on your own. So first things first, we have to show that at least one solution exists. So we have to begin by applying IVT, intermediate value theorem, and then we'll apply Rolle's theorem to show that exactly one solution exists. So let's go ahead and do that. So we consider the function, f of x, which I'm just going to bring the 4x over to the left side. So we get cos of x minus 4x. So remember, we want to set this equation that's given equal to 0, and we consider its function equivalent. So the function we're dealing with is cos of x minus 4x. In order to apply IVT, we need the function to be continuous. Is this a continuous function? Well, yes, we saw this already, where cos of x is a continuous function. It oscillates between -1 and 1. 4 times x is just a straight line, so that's continuous. And we know that the difference of two continuous functions is again continuous. So continuity we have for the reason I just explained. So we have continuity. Great. Now what we have to do is test values to see if we could get one that's positive and one that's negative. So let's begin by testing the value 0, because again here they didn't give us the interval. There's no interval that's given, so we have to essentially just test values. Plugging in 0, we get cos of 0 minus 4 times 0. This gives us cos of 0 is 1 minus 0. We get 1, which is positive, so we obtain the positive answer. Now we have to hope for a negative answer. So what we could do is take maybe, I don't know, maybe pi, f of pi. You could try pi over 2, you could try 2 pi, it's really up to you. I'm going to take pi, so we get cos of pi minus 4 times pi. I know for a fact this is going to be negative because cos lies between -1 and 1, and -4 pi is larger than 1 and it's negative, so I know this is going to give me a negative answer. So taking a large value here ends up working. So cos of pi is -1 minus 4 pi. We know that this is in fact a negative answer. We don't know what it is. If you have a calculator, you can plug it in, but this is in fact negative. -1 minus some value is negative. So we obtained the positive value, we obtained the negative value. By IVT, we know there's a solution in between 0 and pi. So let's go ahead and write that. So by IVT, there exists a C in the interval from 0 to pi. So there exists a c in this interval from 0 to pi such that f of c equals 0. So there's at least one solution c in this interval where we have a root. We have to show that there is at most one c. Okay. So where there's exactly one c. So let's go ahead and apply Rolle's theorem. So let me just erase this and we'll do that. So the interval we're dealing with is c on the interval from 0 to pi. And let's apply Rolle's theorem. So what we do is we suppose there exists two roots. Let's call them m and n in our interval from 0 to pi. Since they're roots, f of m equals f of n, which is equal to 0. They're solutions to the answer. I erased the function, I apologize about that. We have to ensure that the function is differentiable. So we had cos of x minus 4x. We know it's continuous, but is this function differentiable? Could you take the derivative of this? Well, yeah, we could take the derivative of cos and we could take the derivative of negative 4x. So it is differentiable, so that's okay. We have differentiability, we have continuity, and we have the fact that f of a is equal to f of b. All we need is, we have all the statements, sorry, all we need, this implies that we have, at some value, there's going to be a horizontal tangent. Okay, so if we have two roots that exist, such that this occurs, then by Rolle's theorem, there exists a point, let's call it z. There exists a z in between m and n. We'll take m to be smaller than n, such that f prime of z, so it's not like intermediate value theorem where it's f of z equals 0, f of c was 0. Here, Rolle's theorem, we're talking about the derivative. The first derivative is equal to 0. Okay, so if we assume that there's two roots, then this has to occur. There has to be a z in between this interval such that its derivative is 0. Okay, so let's go ahead and take the derivative. So the first function we had, I erased it again, but it was cos of x minus 4x. If we look at the first derivative here is, derivative of cos is negative sine, and the derivative of negative 4x is minus 4. Okay, so we're taking the derivative of this. The argument that we're making now is that this over here can never be equal to 0. Why is that? So think about it. Sine, no matter what x value you put in the sine, it's always going to be stuck between negative 1 and 1. It can't be bigger than that. It's always between negative 1 and 1. Okay, so if you have, let's say, the worst case, negative 1, negative of negative 1 is positive 1. The biggest value you could have here is negative 3. This value here, because you're subtracting this value, which is always stuck between negative 1 and 1, by 4, this is always going to be smaller than 0. Okay, this is the argument that we're making. So sine of x is stuck between negative 1 and 1. So the cases are, the worst cases, you get negative of negative 1 minus 4, which is 1 minus 4, which is negative 3. Or you have the best case, which is negative, just positive 1 minus 4, which is equal to negative 5. So this thing here is always going to be stuck between negative 3 and negative 5, no matter what x value you put here. It's always going to be negative. So if it's always negative, it cannot be equal to 0. There's never going to be a z value, some point where it's actually equal to 0, because this thing is always negative. Okay, so that's the argument that we're making. So that means the assumption that we made that it has two roots is false. It's a wrong statement. So therefore we could conclude that there's at most one solution. So we arrive at a contradiction. Therefore, we must have exactly one root. Okay, and we're done. So this is the argument that we have to make. Okay, so the fact that sine is stuck between -1 and 1, therefore the derivative is always going to be negative. Okay, so I hope this helps, and keep practicing. I'll see you in the next video.